So last time we started talking in section 8.5 about integration by partial fractions. And now we're actually going to do the integration. Last time we basically just learned how to do it or reviewed how to do it. So 8.5 continued. We actually already basically did the first problem that I have for you, so I'm just going to very quickly show you the whole problem. Suppose you were asked to integrate 5x minus 3 over x minus 3 x plus 1 dx. Well, last time, if you look back at your last thing you did in your notes, I gave you this problem without an integral, just said find the partial fraction decomposition. So in doing so, you can reduce this problem down to something you can integrate. Now, how would you know that this is the method you need to use? Well, looking at the integral, it certainly doesn't seem to be anything that's been a method that we've done so far. It's clearly not a trig integral, right? Integration by parts is not going to work, right? That division by things that are undefined, so that's not a transcendental function. Trig sub doesn't make any sense. There's no sum or difference of perfect squares or anything like that. And what else have we done? UDU is not going to really get you anywhere. You could try, but it's pretty unlikely it's going to match up perfectly. So generally, it's not that hard to spot. When you see a polynomial over a polynomial, you're probably going to use partial fractions. Okay, so I'm just going to say that there is, at this point, you'll do a partial fraction decomposition, which we did last time, and it will get you to this point, right? Where basically, you now have found that this thing is equivalent to 3 over x minus 3 plus 2 over x plus 1 dx. Right? So that's the first big part, and the hardest part, I guess, of the problem is done, because we did it last time. Now, once you get down to these baby parts, there is basically a couple things that are going to potentially happen. So you could have something that looks like this, right? Well, actually, I'll just point it out. The thing that we have right now, how would I integrate something like 3 over x minus 3? Well, basically, this is just a natural log, except, we've got a minus 3 in there, a constant, but we can always deal with those by little UDU substitutions. If you use a piece that comes down to something like this, then you're going to have to use like an inverse tan function, right? And if you have some piece that comes down to looking like this, like an x over x squared plus 4, then you're going to end up using basically a little UDU substitution again, right? Well, you make the bottom u, and du will be right on top. And that's really all the pieces that could really happen, right? You're going to break things down into the same types of factors every single time. So you'll see that it's very repetitive. It's going to be logs or inverse tan or a little UDU substitution. That's it. It'll never be something hard when you get down to these steps. Okay, so if I made u on the first one x minus 3, my du would be dx. And the same thing on the second one, right? If I made u equal to x plus 1, my du would be dx again. So really, I guess I shouldn't use u twice in the same problem. So let's just call this v and dv, just a different letter. There's two different integrals here, right? So this one would be 3 over u du, and this one would be 2 over v dv. So you probably don't even need to write this out, because you could pretty much do this in your head. You could think of x minus 3 as the variable that you're integrating with respect to. So I get 3 natural log of u, but that's x minus 3. Do try and remember that there's absolute value signs that go with natural log, plus 2 times the natural log of x plus 1 plus c. And that would be your final answer. All right, so, you could have a question on this either from today's stuff, just integrating, or if you wanted to ask some portion about the decomposition from last time, let me know either way. And like I said, if you are someone who struggles with mechanical stuff a little bit more, trig sub is the bottom of the barrel in the whole class. Okay. Now, I will say this section can get pretty nasty because it can be very long. But again, nothing is particularly hard. All right, suppose we now have, as an example, the integral of 2x plus 1 over 2x plus 3 squared dx. Okay, so again, I don't really see any good way to do this. So trig sub makes the most sense. Notice again, just by a quick note, suppose there was no 2x in the numerator. Suppose it was just 1 over 2x plus 3 squared. Note that in that case, you would just do a u/du substitution, right? There'd be no need to do this all out by trig sub. But because if I split it up into two pieces, the 1 over 2x plus 3 squared would be easy, but the 2x over 2x plus 3 squared would not be easy, because if you tried to do a u/du, you'd have an extra x there. So that's the reason we're going to be going through this method with partial fractions. So let's first of all just deal with the partial fraction piece. 2x plus 1 over 2x plus 3 squared. Note, this is a linear factor, and there's two of them. They're identical, so you're going to use the repeated linear factor rules, which say you're going to have a constant over that factor, 2x plus 3, and then to differentiate it, you'll have a constant over that factor squared. So a over 2x plus 3, b over 2x plus 3 squared. Notice that the common denominator of these two things is what we started with, as it has to be. Now I multiply through by that LCD. So multiply through by the LCD, which is 2x plus 3 squared. When you do that on the left side, of course, knocks out. When you multiply, you get a times 2x plus 3. One of them knocks out, one of them remains. And when you multiply into this term, obviously the 2x plus 3 squareds just cancel out and leave you with b. So I get down to this long equation. Once you get here, now you have to choose which of those two methods do you want to do? The knockout method or setting the powers of x equal to each other method? And actually, in this case, one of the methods doesn't work. So you'll notice that technically I could figure out something for x that would, if I plugged it in, knock out this term. But there's no way to ever knock out the b term. And that's pretty much what's going to happen whenever you have a repeated factor. So I'm not going to really want to go by that method because it's not going to be complete. So instead, let's multiply everything out and we'll match the x's and the constants together. So 2x plus 1 is equal to 2ax plus 3a plus b when I multiply. And then I'm going to look at the terms that have x's in it and the terms that have constants in it to get my systems of two equations to unknowns. So the things that have x's in it, right, how many x's are there? There's 2 on this side, and there's 2a on the right side. Notice I'm not actually writing the x's, because it's a waste of time anyway, right? I mean, this is technically true. 2x equals 2ax, but then you just divide through by the x's, and it'll be gone anyway. So we only need the coefficients when we're writing these equations. Constant terms, I got 1 on the left, 3a on the right, and also b on the right. Now, if you'll notice on this particular problem, there's not that many terms, so it's pretty easy to come up with and match all this stuff up. But you'll notice that I'm underlining each term as I write them in one of the equations. That is useful because in much longer problems, when there's 15 terms left to write, it's easy to lose one. So I just underline them as I write them, so then at the end I know, oh, everything's been underlined, so I've accounted for every term in one of the equations. That's a little pro tip. Okay, so, well, this is actually really easy, right? Because a is just equal to 1 directly, and I just plug it into here. So 1 is equal to 3 plus b, so b has to equal -2. So we got that without much trouble. So that means the integral that I'm going to be doing is a over 2x plus 3, that's 1 over 2x plus 3 dx, minus the integral of b, so I put the minus outside, 2 over 2x plus 3 squared dx. So that's what we've now created this integral into these two little baby integrals, which are pretty easy to solve. First half of the problem done, we've done the partial fraction decomposition. Okay. I'm just going to rewrite it up here. Okay, so same line. So what do I do in this one? Well, you have to be a little careful here. A lot of people get this wrong. A lot of people just say, okay, this is the 1 over linear factor, so ln 2x plus 3. But that's not correct. because if you did the little u du substitution here, dx is not going to just be equal to du, right? If u is equal to 2x plus 3, du will be 2 dx, and therefore this won't work. So u will be 2x plus 3, du is 2 dx, which means I'll have to put a 2 in and pull a 1/2 out in order for me to be able to write the du. So I get 1/2, the integral of 1 over u du. So I end up with basically just 1/2 times the natural log of 2x plus 3. So there's the first integral. Second one is, squared. Second one's actually the exact same u du substitution, right? So I could just actually apply the same things here. I already have the 2 dx exactly where I need it, so it's minus the integral of du over u squared. So this is not a natural log, it's just a power of x in this case. So the integral of u to the -2 power basically is minus -1 over u, right? We can think of this as u to the -2 power, which is you raise the power by 1, -1, divide by that new power of a negative, so you get -1 over u, plus c, and we'll just plug in the u and we'll be done. 1/2 natural log 2x plus 3, minus minus is a plus, 1 over 2x plus 3, plus c. If we were to use x equals -3/2 at the start to remove a, would we get the same answer? Yes, you absolutely would. So you could have solved for a here, and you would have, actually, we could actually just do it real quick, right? If I plugged in x equals -3/2, it's going to get a little messy, but so -3/2 times 2x would be -3 plus 1 equals a times 0, that will knock this out, plus b. So you get that b is equal to -2. Doing this method, though, at that point, you'd be stuck, and you'd say, well, I have to do this out anyway to figure out what the other constant's going to be. But in more difficult problems, sometimes you're going to have to write out the equations, but it's going to be like a system of 4 equations, 4 unknowns, which is really hard. So you might actually do both methods combined and say, look, I can't do the whole knockout method for everything, but hey, if I could get one constant, that's going to really simplify my life later on. So yeah, that works, and they can work in tandem. Good question. Okay, I think we're ready to do the next one. Okay, so integral of 2x over x squared minus x minus 6 dx. And this one's really not that much harder than what we've done at all. But there's 1 or 2 little wrinkles that are different about this than the previous 2 problems. The first little wrinkle is, notice that we have to actually factor the denominator first. It's not factored for us. So that happens sometimes. So this is 2x over x minus 3x plus 2 dx. And then you notice, looking at both of these, it's pretty clearly set up that this is supposed to be something that is integration by partial fractions. So let's go through that steps. Let's first of all figure out what the decomposition would be. So 2x over x minus 3 times x plus 2. Just 2 linear factors, and they're unique. So a over x minus 3 plus b over x plus 2. Multiply, I'm not going to write the multiplication out, but if we multiply through by this LCD, it cancels out this denominator. I get 2x, and cancels out the x minus 3 here, so I get a times x plus 2, and cancel out the x plus 2 terms, so b times x minus 3 over there. Let's just do the knockout method since it will work. They're both discrete linear factors, so if I plugged in x equals 3, I should get 1, and if I plug in x equals -2, I should get the other constant. So plugging in 3, I get 2 times 3 is 6, equals a times 3 plus 2, which is 5, plus b times 0, which kills that term. So you can see I immediately get that a is equal to 6/5. And that's all right. There's nothing wrong with getting non-integers when you do this out. It's a little messier, but nothing too bad. I plugged in -2. 2 times -2 is -4. Equals a times -2 times plus 2 is 0, so that, as we designed, kills that term. Plus b times -2 minus 3, which is -5. So I just have to divide both sides with a -5, and I get 4/5 is equal to b. So now my integral becomes the integral of this decomposition, but I now know a is 6/5. So 6/5 over x minus 3 plus b, which is 4/5 over x plus 2 dx. And now these two are actually very simple little integrals, right? They're just going to both be natural logs, and there's not even going to be a really meaningful u/du substitution with them, recognizing that it is going to be one, but it's not going to really affect my dx du. So I can just do it right kind of carelessly and say that I get 6/5 times the natural log of x minus 3 plus 4/5 times the natural log of x plus 2 plus c. Now, there's a decent chance that they may untest because they probably are asking a little bit smaller questions, right? They may ask you just find the partial fraction decomposition of something, and it may even be a multiple choice answer. So I just want to be aware, if you've got fractions on top, another way that you could have written this decomposition is this, right? I can move the 5 to the denominator as a factor there, and then I don't have like a compound fraction within a fraction, which looks bad. So I could have said this is 6 over 5 times x minus 3 plus 4 over 5 times x plus 2. I'm just going to note this is another way to write the decomposition. And it's a cleaner way. Doesn't really matter if you're going to do the whole problem and just get the integral, but if you just are going to put it in that form, then it's probably better to write it like that. All right, so I'm going to give you guys one to try, which is x squared minus 1 over x cubed minus 2x squared. And as dx. If you do this, you're going to have powers of x here in the factored form. You can see you're going to be able to factor out an x squared. You could think of that x squared term as being like an x minus 0 squared. So it's still just a linear factor that's being squared, and you can treat it accordingly. So why don't we try this for 10 minutes, and we'll reconvene. Should you be getting this? 1/4 log x minus 1 over 2x plus 3/4 log x minus 2 plus c. All right, I'm going to do one that's a little bit worse, I guess. So another example. Negative 2x plus 4 over x squared plus 1 times x minus 1 dx. So this is our first one of the section where we're actually using the irreducible quadratic factors, right? So everything else has been either repeated linear or regular linear. Now we introduce this beast. It's not that much worse, honestly. So it's already factored for us, so that's nice. So let's write the form of the decomposition, which will be, can't factor this because it's a sum of perfect squares, so I get ax plus b over x squared plus 1, right? Remember the rule on this one? There's 2 powers here, so I need 2 unknowns, and since it's a power 2 down here, I can have a linear unknown, which basically means the unknown times an x plus a constant unknown. So ax plus b over x squared plus 1. And then I've got this x minus 1, which is just a distinct linear term, so another constant c over x minus 1. By the way, usually someone asks, obviously there's no right order for what these constant letters are, So someone else could have easily have said a over x minus 1 plus bx plus c over x squared plus 1. Right? Now, they're going to solve for something, and their a's, b's, and c's will be different, but they'll be in the right spots. So just be aware, sometimes if you're comparing notes with a friend, they put their constants on different terms compared to you, and it gets confusing. But it doesn't matter which way you arrange it, and of course it doesn't even matter what you call them. I could have called this W, B, and L or something like that. That's just an FYI. Now, multiplying through, right, by this LCD. So we're going to get, let's write it out. We're going to multiply through by x squared plus 1, x minus 1. For a lot of people, I found doing this all mentally sometimes is a little tricky for them, so sometimes just writing big parentheses and multiplying or writing out what you're going to multiply through makes it a little clearer with the cancellations. Perfectly fine if you always do that forever. So multiplying this in to the left side, you can see the whole denominator cancels out as it must. This term, the x squared plus 1s will cancel out, leaves you with ax plus b times x minus 1. Don't forget parentheses here, because you have to obviously distribute all that. And over here, we get c times the x minus 1s cancel out, and it's multiplied times x squared plus 1. Notice, first of all, that when you have the irreducible quadratic, the knockout method will never completely work. Yeah, there's nothing I can physically plug in here to knock out this term. Right? It's always going to be stuck. However, I'm going to use that method anyway on this term to get the c, and that's going to make things a lot simpler going forward. So note, we can combine both methods. I actually already talked about this due to the good question that was asked before, but now we're officially doing it. We're going to combine both methods. I'm going to let x equal to 1 and see what I get. This side I get negative 2 plus 4 equals ax plus b times, well, when I plug in 1, I get 0 there, so that knocks out that whole term. Plus c times 1 plus 1, which is going to be 2. So at the end of the day, I get 2 equals 2c, and immediately get that c is 1. So that's going to be nice. You'll see why in a second. But that's as far as you can go with that method. So now we have to multiply all this stuff out and create our system of equations like before. So negative 2x plus 4. Now this all has to be FOIL. So ax times ax times x is ax squared. Ax times minus 1 is minus ax. B times x is bx. B times minus 1 is minus b. And then this FOILs, well, I guess just distributes cx squared plus c. So now you can see there's a lot of terms here. So you'll note that in this case, you have x squared terms, x terms, and constant terms. 3 different types of terms. So there'll be 3 equations. And as a nice check for you, by the way, remember that I said the power of the denominator tells you how many constants they're going to end up being, so you can make sure that you didn't mess up. This is a 3rd order denominator, so I ended up with 3 constants. Similarly, the number of constants has to lead to the same number of equations. If somehow that's messed up, again, you did something wrong. So 3 equations, 3 unknowns will allow us to solve this no problem. So x squareds. Question for you, how many x squareds are on the left-hand side? 0. All right, so 0. And how many x squareds are on the right-hand side? A plus c or c plus a, right? These 2 terms are the x squared terms. Perfect. So 0 is equal to a plus c. Nothing wrong with there being a missing stuff on one side, just a 0 then. I'll do the other ones. Again, I'm putting underlines under terms as I go. So minus 2x's, minus ax's, bx's. That's it. And the constant terms are what's left. 4 equals minus b plus c. And there's my set of 3 equations, 3 unknowns. And it's actually kind of a pain to solve systems of three equations, three unknowns. Remember the process is you'd solve for one variable and then you plug that variable into the other two equations, get a system of two equations, two unknowns, work back to get the third one. This one's a little bit easier because there's a bunch missing, but it's still annoying. However, because we did this, we made it actually trivial, right? I know that C is equal to 1, so A has to equal -1, just directly. And if I plug it into the third one, I get that 4 is equal to -b plus 1. Add the b over, subtract the 4, and I get that b has to equal to -3. Probably not a bad idea to just double check that the middle equation still works and you didn't do anything wrong. So minus a is plus 1. 1 minus 3 is -2, and that checks. So we solved, by using the two methods together, we solved this equation. So now we have found that this integral is equivalent to what? Ax plus b, which is minus x minus 3. Yeah, minus x minus 3 over x squared plus 1, plus c, which is 1 over x minus 1 dx. So I'm going to erase all this in a second, and we'll start from here, integrating down. Is the ax plus b something we will always put with this type of problem? That will always, every single time that you have a factor that's an irreducible quadratic, like x squared plus a number, you will have a linear unknown up there. Yeah. The letters might be different, of course, right? Suppose I had an x squared plus 4, then the next term would be cx plus d over x squared plus 4, etc. That always will match with irreducible quadratics. So when you have the irreducible quadratic, you're almost always going to get these two terms on top of it. And what you're going to do is split this up into even two smaller baby integrals, right? Just the x over it and just the 3 over it. So that's what we're going to go towards. And we're really going to solve this. Minus x over x squared plus 1 dx. Minus, I'll pull the minus out, the integral of 3 over x squared plus 1 dx, plus the integral of 1 over x minus 1 dx. So there's the three baby integrals that it all disintegrates into. I'm going to start from this side because it's easiest. This one's like the trivial natural log, right? It's basically 1 over an x minus 1. If I were to make x minus 1 u, du would just be dx, so I don't have to think about it. This just directly goes to natural log of x minus 1. And there'll be a plus c at the end of all this stuff as well. What about this one? Well, if you recall, this is a tan inverse problem. And if I put the 3 out, that's directly the antiderivative of tan inverse. So this just becomes minus 3 tan inverse x. This one is, I guess, not hard. If you were to see this, the first week of class, you should have been able to do it. But it is a little u to u substitution, right? So I would have to make u equal to x squared plus 1. Du would therefore be 2x dx. And I'm basically left with minus, all right, I need a 2 here to make 2x dx, so I'll pull the 1/2 out. So this will be du over u. And this is just going to be a natural log again, natural log of u. So minus 1/2 natural log of x squared plus 1 minus 3 tan inverse x plus log x minus 1 plus c. And there you go, a full, lengthy, full-size problem of this sort of technique. That in mind, I'm going to give you another long, lengthy one. If you got a question, let me know, but I'm going to start writing this one up for you. Okay, here's the one for you. 3x squared plus 2x plus 7 over x to the 4th minus 1. So you're going to have to think about how to factor that difference of perfect squares down there. I'll give you the final answer as well. See, this is pretty lengthy. That's what it'll all turn out to be. So this will take us a good 10 minutes, I'm sure. Just as a quick double check, you should have factored out the denominator to x squared plus 1, x squared minus 1, but x squared minus 1 is, again, difference of perfect squares, which can be factored out to the two distinct linear ones there. So it should be x squared plus 1, x plus 1, x minus 1. Okay, so want to see the decomposition on this? So in this case, you should have 3x squared plus 2x plus 7 over, well, let's do the factored form, x squared plus 1, x plus 1, x minus 1. And again, it's a little tricky because some people will have written these in opposite orders, so the a's, b's, and c's may not line up, like I said, but you'll get the idea. So ax plus b over x squared plus 1, the irreducible, plus c over x plus 1, plus d over x minus 1. When you multiply all that through, you should get this. On the left-hand side, everything cancels out. On the right, I get ax plus b times x plus 1 times x minus 1. I'm actually going to multiply that out because I know that's already x squared minus 1, so it makes it a little easier. Plus c times x minus 1 times x squared plus 1 plus d times x plus 1, x squared plus 1. So, it's a brutal problem of a lot of different terms and such. Let me do the knockout method really quick. So I can get two of the answers just immediately. So if I plugged in x equals 1, I'm going to get 3 plus 2 plus 7 is 12. 1 will knock out this whole term, so that's gone. 1 will knock out the whole c term, so that's gone. And then I'm just left with equals d times 1 plus 1, which is 2, times 1 plus 1, which is 2. So I get 4d is equal to 12, or d is equal to 3. So that's 1 down. If I plug in x equals -1, I'll get another 1. So I get 3 minus 2 is 1, plus 7 is 8. This gets knocked out again, right? Minus 1 squared is 1, 1 minus 1 is 0. The d term gets knocked out, and all I'm left with is the c term. So I get c. -1 minus 1 is -2. -1 squared is 1, plus 1 is another 2. So this looks like -4c equals 8. So c has to equal -2. Then you're stuck. So then at that point, you've got to multiply everything up. Luna does not want to go ahead. She's done. You're done? Oh, yeah. This pointed at the problem. No problem? So she's good. All right, so from there, I think it's just a matter of matching terms and stuff like that. So I'm going to stop it there. If you didn't get, I'm sure there's a few people that made an error here or there and just didn't quite get to the final answer. But I think it's good practice to have a problem you know the answer to that you can work towards. So if you haven't gotten to it, try to get to this spot on your own. We're going to do another whole long problem, so you'll have more practice watching me do the next one. We'll do our worst one of the day, and we've got 20 minutes to do it. I've only seen them give this one time on a common exam, and didn't even like it that one time. So hopefully we don't make it two. Okay. 10x cubed plus 44x minus 19 all over, yes, all over x squared plus 1 times 2x minus 1. Okay, here is why this is such a hard problem. Notice that the bottom is a power 3, x squared times 2x. The top is also power 3. And therefore, since the bottom is not a larger degree than the top polynomial, that makes this fraction an improper fraction. And that means we've got to go do the very long work of polynomial long division. First of all, it's just hard to notice that. So note, I guess I won't say it's hard to notice it, it's just easily overlooked. So notice this is an improper fraction. So essentially, we need polynomial long division first. So we're going to do that part first. That means I'm going to actually have to FOIL this thing out because I need to do the whole long division. So top is the same. Bottom, once we multiply all that out, we get x squared times 2x, which is 2x cubed. X squared minus 1 is minus x squared. 4 times 2x is plus 8x. And 4 times minus 1 is minus 4. So that's the actual original integral. They had to give you the factored form here because you're not going to be expected to factor something that looks like that. You can only really do trinomials. So let's do the long division. This is dividing into this, so it's going to be 2x cubed minus x squared plus 8x minus 4 into 10x cubed plus 44x minus 19. Now, I would suggest to leave placeholder powers of x. So I'm going to actually just erase a tiny bit of this. Notice that there is no x squared term. That's going to make the long division a little bit messy and kind of all slanted. So when there's a missing power in either spot, I would write a 0x squared or whatever the missing power is, because that will allow us to line up all the columns correctly. I'm just going to put a quick note here. To my suggestion anyway, to put placeholders for missing powers. Okay, so now the process of polynomial long division, I'm sure a lot of people just rolled their eyes and said this is going to be awful. It's not that bad. It's actually the same process that you really do with regular long division. You take the leading term here and you see how many times does it go into this term. 2x cubed goes into 10x cubed 5 times. Basically, what times 2x cubed would you need to multiply to get 10x cubed? So I get a 5. Then I take this and I multiply it down by all of the different pieces and line it up. So 5 times 2x cubed is 10x cubed. Those have to be the same. 5 times minus x squared is minus 5x squared. Now, do you see why it's important to have these missing things have a 0? Because then everything lines up. Otherwise, it's going to be a mess to subtract. 5 times 8 is 40x. And 5 times negative 4 is minus 20. Then just like you do in regular division, you subtract down, right? So what I would do, instead of subtracting in your head, because that gets people turned around, is I will change the signs and add instead. So I'll put a minus. This minus becomes a plus. Actually I could just make it a plus, right? This becomes a plus. This plus becomes a minus. And this minus becomes a plus. And then I just add down. And I think that causes less problems. So I'll just mention here, I'm going to say change signs and add, which is the same as subtracting. So these two have to cancel out to 0, that's the whole point. Adding these, I get 5x squared. 44x minus 40x is just plus 4x, and minus 19 plus 20 is plus 1. Then, naturally, the next thing to do is to repeat the process. 2x cubed goes into this leading term how many times? And that would basically be your coefficient here. Now, in this problem, it's over already, because 2x cubed is already a larger power than this, so doesn't go into it at all. So you pretty much stop at this point. So the integral has become 5, right? That's the answer. And then I have a remainder. So 5 plus 5x squared plus 4x plus 1 all over 2x cubed minus x squared plus 8x minus 4 dx. That's the integral that I now have. Good news. Well, I guess not much good news, but there's technically 2 integrals. The first piece of all the results of the partial fraction of the long division should just be like trivial things to integral. Integral of 5 is 5x. I'm going to say save this for later. It's going to be a lot of work until that gets added to the final answer. This, of course, now is a partial fractions problem. All right, now it's a proper fraction, so now I can go about the whole thing. Okay, so any questions with this initial step of the long division? I have to obviously erase this, and we'll do the rest of the problem. Do we revert the denominator back? Yes. So now that I'm going to do the partial fraction part, I already know the factorization, so the integral that I now have to deal with, or the partial fraction piece that I now have to deal with, is 5x squared plus 4x plus 1, and now I go from there. I'm going to erase everything except this random 5x, because that's going to be part of the answer. So you can see the decomposition terms here. Clearly, we've got irreducible piece, so ax plus b over x squared plus 4. And then we've got a piece here that's just linear, 2x minus 1. It's got a coefficient in front of it, but that doesn't make it not linear. Now we multiply through by the denominator, x squared plus 4 times 2x minus 1, and I get this. 5x squared plus 4x plus 1 equals ax plus b times 2x minus 1 plus c times x squared plus 4. And I could plug in right now and get the c. I'd have to plug in a 1/2. I actually don't personally think that's a great idea, because now I have to deal with all fractions in here. So let me just try and get a 3x3 system and solve it straight up. Of course, you could plug in the 1/2, but fractions give people more fits than they're worth sometimes. So multiplying, foiling in here, I get 2ax squared minus ax, distributing the ax in, plus 2bx minus b, and then distributing here, I get cx squared plus 4c. Now I've got 3 equations for my 3 unknowns: x squared factors, x factors, and constant factors. The x squareds are 5 equals 2a and c. The x's are 4 minus a, 2b, and the constants are the rest. 1 equals minus b plus 4c, and I used all the terms, so I'm good there. All right, so let's try and do this system of 3 equations, 3 unknowns. What you generally do is you solve for one variable, c equals 5 minus 2a, and I plug it into the other 2. Doesn't matter which to which, but basically that is the process to get a system of 2 equations with 2 unknowns. So when I plug into equation 1, I get this. I'll do, it doesn't. When I plug into the x equation, I get 4 equals negative a plus Well, there is no c in that one equation, so that's fine. That equation is itself. And when I plug this into the last one, I get 1 is equal to negative b plus 4 times c, but that's 4 times 5 minus 2a. Or I could say it's 1 equals minus b plus 20 minus 8a. Now I've got two equations, two unknowns. So I could say that this is like a 2 by 2 system. And I've got to plug in, solve for one variable, plug into there. So maybe I'll solve for a here. I got a is equal to 2b minus 4. And I'll plug that down into the bottom one. To get 1 is equal to minus b plus 20 minus 8 times a, which is now 2b minus 4. And now I can solve for b and then just like work my way up the line to solve for a. So what do I get here? 1 is equal to minus b plus 20 minus 16b plus 32. That's right. So minus b minus 16b, that's 17b, if I add it to the other side, is equal to 52 minus 1, or 51. So it looks like b equals 51 over 17. That's, that is 3, right? So b is 3. Now I can work my way back up the line. A has to equal 2 times 3 is 6 minus 4. So a is equal to 2. And working back up the line still, I get that c is equal to 5 minus 2 times 2, so 5 minus 4, c is equal to 1. So I've solved the system. Of course, what's left over is I still have to actually do the integral. The integral at the end of the day is equal to, and this is a little tricky, remember there's that 5x from that one little piece from the polynomial long division that's still there, that's part of the answer, plus the integral of ax plus b over x squared plus 4 plus c over 2x minus 1 dx. And now I've got all those pieces, so I could say my original integral was 5x plus a, which was 2, so let's just say that's 2x over x squared plus 4 dx, plus b over that, which was 3, so I'll put it as a separate integral, 3 over x squared plus 4 dx, and then c, which is 1, the third integral, 1 over 2x minus 1 dx. So that's all the baby little integrals. So now you can see why I said that this section can be almost just as annoying, maybe even worse, than the last one, even though I think it's easier. It's just like a lot of grunt work, potentially, to get to this answer. Okay. I don't think we have time to do this thoroughly, but I'm just going to mention what to do in each of these cases. Obviously, 5x is part of the answer. This is just a simple u du, right? If u is equal to 2x plus 4, du will just be 2x dx, and this is going to be a natural log that comes out of this one. This one is going to be an inverse tangent. However, notice that it's not x squared plus 1. So we have to recall the generalized formula of inverse tangent. So remember, if I have 1 over u squared plus a squared du, that's equal to 1 over a tan inverse u over a. Right, so the a in this case is a 2, so it's going to be a 1/2 tan inverse x over 2. And this one is just a simple log. There will be a little u du substitution in there, but the final answer is going to be this. 5x plus the natural log of x squared plus 4, 3 over 2, right? The 3 is a constant, the a is the 2, so plus 3/2 tan inverse x over 2, and this piece turns out to be 1/2 with the u du substitution, natural log 2x minus 1 plus c. So yeah, kind of a brutal problem. And just so you know, just so you don't forget, I do plan to make this homework, I'm going to make it due on Wednesday, because I think these two sections are the most work of all the sections. So I don't want you to have to work like 8 hours on Sunday or something like that. So the other ones will be due on Sunday, and then this one will be due on Wednesday. Otherwise, quiz on this stuff on Wednesday morning, and business as usual. If you got any questions, let me know. I'll stick around till 4 o'clock. The next exam is several weeks away. We just had it, so.
Have a nice day.
You too. I'll let you know, when in advance for the exam. Guys, bye.